Hey everyone, and welcome to another LeetCode problem. So today we're going to be doing problem number 489, Robot Room Cleaner, and it's a backtracking problem. It's a hard one. It's probably one of the hardest backtracking problems I've done. Even if you know like backtracking, there's a lot of annoying parts of this problem for sure. So I would encourage you, if you are learning backtracking, it is on the backtracking explore card. I would encourage you to try this one for sure. Um, just to test your, understanding of backtracking. And the hard thing about this problem is, I'll just tell you, is so you have this robot in a grid, and you don't know, you're not given access to the grid. The only thing you're given access to is a couple functions for the robot. So you're given a move function that will return true if the robot can make a valid move, and then you can turn the robot left and right, and it starts off facing up. And so yeah, the annoying thing is like you don't see the grid, you don't really know where the robot is, and it's hard to visualize if what your algorithm is doing is correct. Also, the other annoying thing about this backtracking is, like, let's say you're in some cell. Like, let me draw a grid here. So let's just draw a simple grid, 3x3 grid with no obstacles. Okay. And let's say here's our robot. Just make a circle, it's going to be facing up. So the annoying thing is how to figure out, well, how do I actually backtrack? Like, let's say I call move and the robot moves up here. It's still, so whenever you move, you're still facing the same direction. But how do I actually backtrack? Like what's my backtracking algorithm? Like, if I return, it's still going to be in the wrong grid. So how do I even do this? Okay. And so what you're going to want to do, if you can visualize, I mean, when you go somewhere, your end state needs to be, your robot needs to turn around, right? So it needs to face this way, and then you need to call move. And then you can handle backtracking one of two ways. So you can either move back and then return, and then like turn it around in the function right before you return, or you could handle it in the actual backtrack function. So let's say you just call backtrack, right? You call backtrack with some, you move and then you call backtrack. Then what you can actually do is, once the function before returns, like let's say this function, you call backtrack, the robot's over here, and then it's looking the way you want it to. Let's say for the ending state, maybe you want it to look like this. I don't know. There's a bunch of ways to do it. Then what you would have to do is, well, what would you have to do to make this state turn into this state, right? And this is our original state, and to fully complete our backtracking. So in this case, we'd have to turn left or right twice. So let's just say turn left twice. So we can just call that function. Then we have to go move, and then we have to turn left again twice. So hopefully that makes sense. When you have this robot, you turn it around. So a 180-degree rotation would be left or right twice. Then you'd call move, then it would go here, and then you'd turn around again, and then that would give you the original state of the robot before it entered this. So this is how you would get out. Now the other annoying thing for most backtracking problems, well, it actually depends, but let's say you do have some backtracking algorithm, and let's say your backtracking algorithm so let's say you try the cell in front of you, and then if it doesn't work, you just keep turning right, and you keep turning right, and you keep turning right. Well, let's see what would happen. So we can't go here, so we're gonna turn right. Okay, and remember, when we go into a cell, we face the same direction that we came in. We can't go here, we turn right. Just going down. Okay, we can go here. Okay, we can't go down here, so we turn right. Okay. Can't go down here. So we turn right here, then go over here. Okay, well, now we can't go here, we go here. So how do we even know, and then we end up here? How do we even know we ended? Like, we don't have a grid, remember? And in this case it worked out, but in other cases, you can try out some other examples. But in some other examples, when you do this, when you just keep turning right, so in this case you did end up where you started, but in a lot of cases you'll just run into like a loop. And how do you even know? And then you just hit maximum recursion depth, right? Because you keep looping, but you don't even know that you cleaned every room, and you can't check that you cleaned every room. You don't know how big the grid is. You're not given access to any of that information. All you can do is move the robot. And so how would we solve that problem? And to solve that problem, this is also kind of really annoying. Actually, what we're going to do is we're going to have a visited set. And you may ask, well, how do you have a visited set if you don't even have an index of like where you're starting? And so what we actually need to do that makes this problem difficult is you have a visited set, and then you need to figure out what index, at least what relative index you're at. And so let me show you what that looks like. So let's call this index 0, 0, right? So we just say inertial index is 0, 0. So we put 0, 0 in here. And now, by the way, when we traverse, we're going to only traverse if the place we're traversing isn't in our visited set, because we don't need to visit the same room twice. Also, for this backtracking, that makes it different from some other ones, like a Sudoku, is even if you, like, once you're on a path and you go to a bunch of rooms, when you backtrack to where you started, you never have to go back to any of those rooms again, because we've already cleaned them and we've already went as far as we could from any of those rooms. So once we have a visited set and we add items, we're never going to remove them. In a normal backtracking, you normally do remove, and you kind of check for a final solution type of thing, you know, like for end queens, you would go down all the rows and you have to see, is there a final solution? And you would keep removing queens from the set. But in this case, once you were in a room once, you never have to clean it again, because as soon as you go into a room, you can just hit clean, and then it's clean. So let's say we're here. So what we're actually going to use is we're going to use so to actually use this for a lot of DFS. So we're actually going to have an array like this of directions, and we're going to, so normally when I have this array of arrays for different directions, I have like 1, 0, 0, 1, negative 1, 0, and so on. But here, the mistake we need to not make is we need to make sure that, so we're going to be turning right a lot. And now we need to figure out what are the values that you need to go up, and then if you turn right, we're going to try to make sure that the value to the right of the current one we're at is the right thing. So to go up, actually, it would be this. We are going up a row. Now, if we're going up and we turn right, now what is this? This is column plus 1. And so this is another tricky thing, is you have to make sure you arrange these in the right order for this problem. So this is going to be 0, 1. Okay, now down if we go right. So down is 1, 0. And then, so yeah, if you do normal like stuff that you use for other functions, you're going to get an error. So now we were down, now we need to go right, or sorry, left, right? So down, if we turn right from down, it's a left. And left is actually 0, minus 1. And so this is what it's going to look like, and all we're going to do when we turn right is we're just going to say, let's just go to the next direction. Right, let's go to the next direction, and when we reach the last one, we can simply just go back to the first one. So let's see what kind of that looks like. So we're at 0, 0. Now we know we're going up. So if we're going up, that means our row is minus 1, right? So then that would be negative 1, 0. And so this index, I might cut out for a second. So this index is going to be negative 1, 0. Now we tried to go up, we can't, we go right. So then what is right going to be? Well, right's going to be negative 1, 1, and so on. So you're gonna have these relative indices instead of absolute indices. So even though you don't know how big the grid is, you have to know which way you're facing and where you started, and from there you can figure out what relative index you're at. And so we're going to keep adding to our visited set until we can't go anymore. And then we are going to, like I said, when we're facing some direction, so it's going to look like this is what a backtracking would look like for just one particular square, right? So if we have a square, let's say we came from here. So we came from here, we're in this square. Let's say we can't go anywhere. So we try to go here, can't. We turn right, try to go here, can't. Turn right, try to go here, can't. And because we can't, because it's visited, then we turn right again. And then we try to go here, and we can't, and then we turn right one more. I'm going to double check the code, but our ending state wants to be like this. So after we tried everywhere, we want to be here. Yeah, so actually, first we don't turn right, so we turn right 4 times total. So we try here, we can't, try here, can't, try here, can't, try here, can't, and then we turn right one last time. And so we turn right 4 times total, and if we turn right, we make 360 degree. And then once we're actually going down here, then we simply, to go back, like I said, we turn right twice, so then we turn around and we go this way, we hit move, so then we're back in this cell, and then we simply turn right 2 more times, either, and you can do this either in either method, as long as you do it, because even once you're back in the original method, you can actually hit move, and if it's like an invalid location, as soon as you've as long as you've cleaned all the cells, it doesn't really matter. Like if you try to move and you recurse back to the original method, it'll be fine. Okay, so let's take a look at the code and let's explain it. So I actually didn't want to code this up on the fly because there are definitely, there's not a lot of code, but there's a ton of errors you can make here. Okay, and so like I said, these are the directions. So this is representative of up, then we have right, then we have down, then we have left. Oops. And we have a visited set, and then we have this backtrack function. So first thing we do when we get into a room is we clean the room. Right? So as soon as it doesn't hurt us to clean the room, so we might as well do that. Then we add that room to our visited set, and then here's our loop where we try every single direction. And so to get a new direction, our initial direction is going to be up, which is going to be this thing right here. And so to get a new direction, we're just going to have an I in a range 4, and then we are going to do direction plus I mod 4. And what that does is it starts at 0, right? So the original direction will be this, then it'll add this, then it'll add this. But let's say our original direction is 3 maybe, so we're on this one. Then if we add 1 and mod it by 4, it'll actually loop back to the beginning of the list. So this makes sure we're not out of bounds, and then we just loop back to the beginning of the list. Then we calculate a new row and a new column based on the direction we're at and the current row and column we're in. And then remember, so this is also another thing you can screw up. When you do this check to make sure that your row and column isn't in your visited set and this robot move, make sure that you check that the row and column isn't in the visited set before you do this robot move. Because if you do the robot move, now you're going to be in another square, and then you're not going to, like, this stuff isn't going to line up. So you have to make sure it's a valid place to go before you even try to go there. Otherwise, yeah, like even if you can't go there, it'll be fine. But if you can go there and it is in your visitor set, that's going to screw up your code. Okay, so now we backtrack to the new direction and new row column. Then remember, when we backtrack, this is when we are recursed out. So in my code, I made it do this 180 right after you leave the backtrack loop. You can do this in a bunch of different ways. And then we turn right, so we turn right 4 times, as I said. So really what's going to happen is this is going to be when we return from a square, right? So let's say we were in this top square, we went down, right? Then we returned from a square. Well, the way my code works is when we're returned, we're actually going to return facing the other way. And so when we return, we just need to 180 it around to be in the original state we were in before we backtracked. And so that's what that does. So turn right, we check, remember we check the next place we can go to. And then this is simply what we do before we backtrack out. So when we, and like I said, I could have done, I'm pretty sure if I wrote this code, in here, this would have worked too. I don't want to test it. Actually, we can do it. We can try to test it. So let's just see. Let's say we backtrack out, and we literally do it right here instead. What happens? Might work. Maybe there's some other thing that I need to think of, but okay. So it actually does work. So that's another way you can backtrack out is. So now what I did instead of my original thing is I have something like this. And so let's say I'm here, and now I would be actually, let's see here. So I turn around twice, and then I move. Yeah, okay. So I believe that the final state is like this of the cell that I backtrack to. So what I need to do is I need to turn it around, right? Then I need to move back, and then I need to turn it around again, and that would make it the same state here. So, like I said, you can put this code in multiple different places. But basically, yeah, you have to make sure you handle this and turn right, turn right. You know, you want to turn right as many times as you turn left so the gears on the robot, you know, don't get rusty. You don't want to keep turning right only. Okay, so anyway, So yeah, so you go back, and then this is the initial function call, and I just made it pass with 110 because, and so what I would encourage you to do, by the way, if you're getting a lot of errors, is maybe one thing that helped me is this grid is really big, so you can just make a custom grid, and you can even try something like this, where you have a custom grid, and this is the custom grid I used, where every cell doesn't have anything, and then I just made all of these ones, one meaning it doesn't have bricks, so it needs to be cleaned, and then I made my starting location this, and then I would try to draw out the states of the robot on my grid, and then also print like the visited set and where I was in, and make sure it matched, because that's how you catch a lot of your errors. That's what saved me a lot of time for sure. So and you can also do that by, if you don't know, in this new LeetCode version, what you can actually do is you can go to test case, you can add a test case, and so you can say, like, if you know what it looks like, so something like this, you can add that in, copy that. So this would be a 3x3 array if you wanted to, and then you could say, yeah, like start at 1 1, and maybe print my visited set or row column or whatever it is when you have errors. Because, like, if you think about it, there's no really way to test for this. What makes it really annoying and difficult is there's no really way to test your code. Like, when you have a bug, it'll just say all the rooms weren't cleaned, and you don't really know where the robot was or where it went because you have no access to the grid. So it's a real pain to try to debug it unless you actually draw out the grid yourself and try to follow, like, is the robot facing the right way? Is it going in the right order? By checking where the visited set is and where the column is and so on. And so I do think this is a great problem for backtracking. It definitely does get annoying with you have to do a lot of visualization and figure out what things have to look like with limited information. So okay, so let's do the time and space complexity. And actually, the time and space complexity for this problem are pretty good compared to a normal backtracking algorithm. Normally they're very inefficient. And so here, because we're never actually removing from the visited set, we're not visiting a cell more than twice. So we are only visiting cells that are ones and not, so let's say 0 is a brick, we're only visiting cells that are ones. So it would be something like count ones minus, or it would just be count ones, right? So if we have whatever many empty cells, we only visit them one time. We do have to technically go back, actually, but I think that is not going to add complexity, so that's fine. Okay, and as far as the space, so what did we do for space? So we do have this visited set, right? And so this visited set is going to have every single, so this is kind of the same thing. It's going to have every single room we visited, but we can only visit rooms with count ones. So that's just going to be big O of count ones. And yeah, like I said, if we clean a room and we backtrack, I think that should be constant time to backtrack back. Or, yeah, it's actually going to be, no, it's actually going to be like big O of, so we do actually have to visit a room and we backtrack back. So let's say we go something like this is our path, and we have to backtrack back. How much does that cost? Like, our maximum call stack does get to like the number of rooms we visited, but we're basically just visiting a room and then coming back, so it's going to be like big O of 2n instead of n. It's not going to add anymore. And then once we did visited these rooms and come back, we can never go into any of these rooms that we visited ever again, because we're never getting rid of them in the visited set. That's what would make things more expensive, and that's why most backtracking operations are more expensive, because you have to fill in, let's say, 9 different problems, and then you can have repeated work, where here you can't. Once you visit a room, you're done. Okay, so that's all for this problem, and if you like the solution, please like and subscribe to the video. It helps grow this channel, and I'll be posting more in the future, so I'll see you in the next one.